Yeah, thank you so much. Thank you all so much for coming and for joining. I don't think I've actually given a chalkboard talk before, so I apologize in advance, especially for my spelling, my terrible handwriting, for standing in front of the board so that you can't see, and for erasing things that I will later need. So this is going to be kind of a lightning overview. I should turn this on. Can we tell? Is it? Yeah, okay, just going to go. All right, so we're talking about gravitational waves in a new low-frequency regime, the nanohertz regime, where we think we're sensitive to massive black hole binaries and supermassive black hole binaries, and we think we've just detected something. So if we're going to talk about this, we unfortunately have to start at the very beginnings. So let's think about gravitational waves in general relativity. So the way that we describe space-time gravitational waves is through a metric, where we define a space-time interval and an invariant in terms of a metric that looks something like this. And in the case of flat Euclidean space, when you have nothing interesting going on, then this metric takes the form of just the Minkowski metric. And this is very nice, where everything is mostly rectilinear as long as we're not moving quickly. Dx squared, dy squared, and so on. So the idea with gravitational waves is that we can always be very, very near this flat space-time, and we can say that our metric looks something like this flat space-time with some perturbation to that. And I'll end up showing that this is how we describe the gravitational wave. So in general, the only criteria here is that h needs to be a lot smaller than eta, and this is usually, we have a pretty good 10 orders of magnitude. So this is 10 to 20 orders of magnitude, so this is usually a very safe approximation. So in this way, we kind of linearize gravity. We take Einstein's equations and linearize them in this perturbative approach. We find that there's a wave equation that this portion of the metric needs to obey, and we can find plane wave solutions. So I'm skipping over a lot of things there, but in general, we'll be able to write this metric as just some amplitude here. And then what's interesting about gravitational waves is that they allow for these polarization tensors that all, so you are allowed two independent polarizations for your gravitational waves. We usually parameterize these in terms of linear polarizations, plus and cross. You can express them in some way. I'll kind of describe that in a second. But so this just looks like plane wave components. We have an amplitude for each of those different polarizations, right? Okay, and then this is some oscillatory component. I guess it would be helpful if this is the wave vector. So this looks something like, we can identify the time component with the frequency, and then we have the remaining directionality of that. So that's just how we describe the parameters of this gravitational wave, and that along with the amplitude is really all that you need to describe it. Okay, so if we pick a particularly nice geometry where the gravitational wave that we're looking at is just traveling in the z direction, and then we can write out what this metric looks like, writing out the full thing. Lots of zeros in there. And if we just take the real part to look at observables, then this will be something like a cosine with an arbitrary choice of normalization, like that. So we have two amplitudes for the plus polarization here, A plus, and we have an amplitude for the cross polarization there. Okay. So the way that we describe motion in general relativity is using the geodesic equations. And that looks something like this. We have Christoffel symbols over here, some other stuff. These Christoffel symbols depend on the derivatives of the metric, and in linearized gravity, those all go to 0. I'm sorry, there's an important equal sign on the other side there. So in this linearized gravity, we have this solution, and that actually tells us something very important, that in terms of our coordinates, our space-time coordinates, the motion of objects remains fixed before, during, and after gravitational waves passed. And this was something that really confused me in my intro GR. But so our coordinate positions in motion stays fixed. Now that's very different from our proper motion. So let's calculate our proper distance. So our proper distance s, we need to integrate over our trajectory, our geodesic. We have a g mu nu, dx mu, let's call that t. One half, and then if we plug in the particular form of our metric for this geometry that I derived, and let's further say that we're considering a proper distance along the x-axis. So we have one object at position A, another one at B. This is some coordinate distance LC apart from each other. So that, again, the coordinate system, the coordinate distance remains the same. We want to see how the proper distance varies. So this is 1 plus h plus of t here, ds to the 1/2, and that's approximately, I'm sorry, so this is the proper distance there. We get something like 1 plus 1/2 of that strain, something like that, okay? So our proper distance does actually oscillate with this gravitational wave as it passes. And just to be very clear, so I said this gravitational wave was moving in the z direction, so that's into or out of the board. And we're looking at a separation within the board, so perpendicular to the direction of motion. And now it's very useful to define the strain, which is the fractional oscillations of space. So we have something like delta L. Actually, I'll write this somewhere where I can keep it, right? P over L, and this can be LP or LC, so we're thinking about the distance in the absence of something, and that looks like just h plus cosine 2 pi f of t. Okay? So here we can very clearly identify that the strain, this thing that we usually write as h, is really directly identified with just the magnitude of these wave components. Okay? And we can also write this in terms of, we can do the exact same calculation switching to light travel times and measure the deviations in times. And that's what our experiment ends up doing. So this is equivalent to delta t over t. Is there a question or comment? Okay. So we can also do kind of this same exercise for a whole ring of point masses. So let's say at a phase of 0, we just have an unperturbed ring of point masses here. Now, as that moves forward, we start to oscillate these in orthogonal directions. So this is how those point masses evolve over time. Okay, so we've got this squishing and stretching. This would just be the plus polarization. The cross polarization is just 45 degrees rotated, and so that's how this metric changes in time. Okay, so our experiment uses pulsars. These are pulsar timing arrays. So the idea is that we have a bunch of millisecond pulsars distributed throughout the local galaxy, and we measure the times of arrival of their pulses and look for deviations in those times of arrival to measure this local metric strain. So let's consider a more general geometry. We have a pulsar here, and this pulsar is sending radio waves along some path, everybody's favorite Greek letter xi, down to the observer, the origin here. So very generally, we can write that here the change in arrival time, so the difference between the actual arrival time and the arrival time in the presence of a gravitational wave, delta t, will be 1/2 just the unit vector towards that pulsar times our metric along that path. And so we need to go from, we start at 0 time at the position of the pulsar, and we arrive at some time t at the origin. So that's the trajectory that we're integrating over. Now it ends up being much more convenient if instead of looking at timing delays, we look at the redshift of this, which is just the derivative of timing delays over time, a little weird, dt. And that's the same thing as kind of a classical redshift. If we have some frequency of pulses being emitted from this pulsar, it's just how that changes in time here. So that, we just put in a derivative here. So let me actually take that out. ddt there. And in full generality, you can't really simplify that further. You would just need to calculate that analytically if the gravitational wave is changing in space and time. But usually we can assume that we're very far from sources. The amplitude and the frequency are going to be relatively constant. So we can do some cool geometry. And I'll skip the actual geometry, but we can express dH dt as c over 1 plus, this is kind of a projection of the path of the photon along the pulsar direction, dH ds, which makes that easy to integrate. So let me actually stop here and emphasize a few points. So the strain pattern, that's quadrupolar. That's perfectly quadrupolar. And then that's being projected onto the pulsar components there.
But the light or whatever radio, because it's a packet, or how good the count.
How reliable are those?
No. Where you count? Where is the beginning and where of?
Oh, arbitrary. We're always looking for deviations in the timing. Oh, what is producing?
Periodic pulse.
Yeah. So what the pulses look like.
I see. So it's a short.
Something like this. Yes, very short. Yeah. So the width of these pulses is something like 100 nanoseconds or so, and the period of these is milliseconds. Let's say like 10 milliseconds, something like that. And we observe these for tens of years. A lot of different various time scales here.
How far away is it?
Kiloparsecs, thousands of light years, typically.
Thousands
Local
of light
galaxy,
years.
yeah.
You said the period was nanoseconds, but that's like
Sorry,
30 years.
Sorry, the arrival, the burst is nanoseconds. The interval between pulses is milliseconds.
But you said you were seeing frequencies of nanohertz.
Yes,
and
right.
that corresponds to about a 30-year period.
Yes, that corresponds to our
Coming from
observing
thousands-
duration.
It's coming from thousands of light years away. Why doesn't it just integrate to zero?
For this reason. So we plug in for dH dt, we can re-express that as this, and so it ends up just being the I'm about to write it, so I'll write it in just a second.
Okay.
So the point that I wanted to emphasize, the strains are quadrupolar. They're directly projected onto the pulsar positions. But here, if we look at the time-integrated effect on the pulses as they propagate, this is no longer quadrupolar. Okay? I think that becomes a little bit more clear if I actually write this down. D delta t z. Okay, so we get pi hat, p j hat, we still have 1/2, 1 plus k hat, p hat, I. And then, so now we just evaluate the strain at the two endpoints of this integral. So this is evaluated hij at t0 minus hij at t minus LC over C. So this is the retarded time coordinate for the strain evaluated at the position of the pulsar. Okay. So there is an oscillatory part that does cancel out, that integrates out, but you're still left with a residual at the endpoints of this integration. So you're just sensitive to the difference between the two endpoints, the difference in phase between the two endpoints. Okay. And so this term is no longer quadrupolar, okay, and that's crucial to the PTA experiment, right? So if we, in particular, if we consider k equals p as opposed to k is in the opposite direction of p, so this is a gravitational wave coming from the direction of the pulsar or going against it, this is no longer symmetric. So you might be worried that we have a singularity. We don't, because the numerator turns to 0 also. And that's because as the photons are propagating, as the radio waves are propagating from the pulsar to the Earth, if they're co-aligned, then the radio waves surf the same phase of the gravitational wave, so they necessarily arrive at the same phase that they left with. So this term is 0. So we get a redshift of 0 when they're co-aligned. Now, when they're anti-aligned, we get some phase depending on the light travel time, right? So actually, the radio waves are moving opposite to the gravitational waves, so they're moving twice as fast through the phase angles. So there's this difference in information between the two sides. Okay, so we call this the Earth term, the strain at the Earth, the time of detection, and this is the pulsar term, the strain at the pulsar evaluated at the time that the gravitational wave passed there. Okay, so what's crucial about this is that this is a very unique signature to gravitational waves. So we can form a correlation between two different pulsars on the sky that's going to have an imprint of this particular pattern. So if we look at some correlation between a pair of pulsars, let's say P and S, and we'll look at a correlation as a function of time with 0 delay between the two pulsars, then that's just something like, so we're integrating over some total observing duration, those pair of redshifts from pulsar P and pulsar S over TT. And then, so even if we have some noise component, or actually, yeah, let me rewrite this a little bit. So we have that redshift. We can re-express this. Let's call this an antenna response function, just some letter to represent that. F times h at the Earth minus h at the pulsar. And then we can also have some noise here. Right? And so for a pair of pulsars on different points on the sky, this pulsar term here is going to be uncorrelated from each other because they're at different distances, they're at different sky positions. So the pulsar term is uncorrelated. The Earth term is going to be exactly the same. Yeah.
How do you determine the delay LC, for example, if there are other gravitational sources present?
So this would be for each plane wave that we're considering. So at the end of the day, we're interested in a background of a huge number of sources. So it'll be some superposition of these plane waves from all sky directions. But in practice, it does depend on exactly the relative orientation of each pulsar in the source. Okay, so the pulsar term and the noise are uncorrelated. The Earth term is correlated. So our expectation for this is that it's just going to end up being something like this, the Earth term from pulsar P, Earth term from pulsar S over our total observing duration, Earth term of the strain squared dt. And now, if you average this over all sky locations of sources, or you average this over all different pairs of pulsar locations on the sky, you get a very important, famous result shown by Hellings and Downs in 1983, pretty sure, 90% sure.
Yes.
Thank you. Great having experts in the audience. So we can say that the average value of this correlation is going to be just the power of the gravitational waves at the Earth term times this function that ends up being just a function of the angular separation of pulsars on the sky. So nothing else matters except for that angular separation. And what that ends up looking like, we look at correlation, rho versus angle between the pulsars on the sky. So we have pi, 2 pi, nope, can only go halfway, pi. And it looks something like this, okay? Where the maximum correlation is 1/3. On the opposite side, it's 1/6, and something like minus 6-ish in between there. But this is really primarily coming from that quadrupolar response. So if you have two pulsars lined up near each other, as the gravitational wave is being stretched in that direction, they're going to be correlated if they're close together. If they're at near 90 degrees, they're going to be anti-correlated. One side compresses as the other stretches, and as they go back to the opposite side, they're again correlated together. The reason why this isn't symmetric is because this response is no longer quadrupolar, and there's different information content if you're moving with the wave or against the wave. Okay. So what's really exciting, forgot to start my stopwatch, is that in 2023, multiple pulsar timing arrays across the world made measurements of this correlation, and they looked like that. So the error bars are still relatively large, but they perfectly match the expectations. We see positive, negative, positive correlations. We see zero crossings at roughly the right places. And if we calculate what our false alarm probability is, we get something like 10 to the minus 5 to 10 to the, oops, that's not a 5, 10 to the minus 5 to 10 to the minus 4, depending on how you calculate this. And that corresponds to a 3.5 to 4 sigma type of detection. We have lower standards than particle physicists, so we feel pretty good about this. Okay, I'm going to skip a bunch of things. Let's talk about, go ahead.
I mean, this is an average over sort of a thermal average over gravitational waves.
Yeah, so
the calculation,
the calculation works either if you have a single gravitational wave source and you average over an ensemble of different pulsar pairs, approaching an infinite number of pulsar pairs, or if you have an infinite number of sources distributed uniformly isotropically across the sky and a single pair of pulsars.
Can you say that, restate that again one more time?
Yeah, so there's a symmetry between the different angles of the system. Either you fix your pair of pulsars, or you fix your gravitational wave location. As long as you average over one of those, you end up getting the Hellings and Downs correlation. So this correlation pattern is not unique. You see this for a gravitational wave background. You also see it for an individual source with an infinite number of pulsar pairs. The amount of variance will be different. Sorry?
When you're seeing fixing one versus the other, I thought it would be fixing the
No,
same
it's
thing.
different. So let me ask you, Luke, how many pulsars?
Yeah, so
And it would be helpful, I think, for some to give a brief diagram of the galaxy relative to the pulsars.
interesting. Yeah.
But could it be some special distribution which would give you a different correlation?
Yes, you can construct something, but the probability of having that is very low. So that's what's being checked when we're looking at these null stream analyses. So yeah, to describe the galaxy, we have, spirals, right? Something like that, and there are lots of stars in your galaxy. We live over here. It's always plotted in the same place. I don't know why. We live here. We can't actually see our galaxy, it turns out. But these pulsars are distributed in like roughly a spherical distribution. They're concentrated more towards the center where most mass is. So you have all of these different pulsars. These are different from the stars, clearly. Here, and then every pair of pulsars, you construct a correlation between those pairs, and then between those pairs, and between those pairs. So in the fifth nanograv, nanograv is the North American Nanohertz Observatory for Gravitational Waves that many of us are a part of. The 2023 paper was our 15-year results, where we had 68 pulsars in our data, analyzed 67 of them, which is thousands of pulsar pairs. And the variance between those pairs is where these error bars come from.
Yeah. But you can take, a certain angle, where to look, and look different, kind of selection, right?
We can't really point pulsar timing arrays because this Earth term is going to be the same in all directions. Yeah, maybe we can talk more afterwards. I'm not sure. I might be misunderstanding.
Maybe it's a question about the background that we assumed here is necessarily isotropic.
Yeah,
So you
right.
see the same
Yeah,
stochastic signal in all of the pulsar pairs if you make the assumption that the background is isotropic.
Okay. Now let's talk a little bit. I want to keep that. This can probably go. Let's talk about the sources. So it turns out that binaries are basically the perfect gravitational wave factory synthesizer. That's the word. They make gravitational waves really well. And so, Einstein long ago derived an equation to get kind of the luminosity of gravitational waves as a function of sky angle. This ends up being proportional to the third time derivative of the quadrupole moment tensor times that polarization tensor. And this is also proportional. Is there a squared on that? Yeah. That's squared. And this is also proportional to the first time derivative of the strain squared. And this quadrupole moment tensor, that's very simple for a set of point masses. It just looks something like, xij times the masses. You're summing over the different masses. We can assume, I'll show that it's okay to assume that these are just in nice Keplerian orbits, binaries. And so we can get out that the luminosity of these gravitational waves, assuming a circular binary, is just proportional to a quantity that we call the chirp mass to the 10^3, and the gravitational wave frequency to the 10^3 also. This chirp mass is a product of the two mass components, or the total mass and the mass ratio, dimensions of mass. And then we can re-express this in terms of the strain to get that the typical strain, and I'm just denoting that this is a binary circular strain. It's going to be something like 8 times 10 to the minus 16 chirp mass over 10 to the 9 solar masses to the 5/3. Gravitational wave frequency at 6 nanohertz to the 4/3. And co-moving distance to the source of about 500 megaparsecs, minus 1. Okay, so that's kind of the typical strain amplitude that you expect to get from a binary that has a mass of roughly 1 billion times the mass of our sun. It's orbiting with periods of about 5 years, 10 years, 10 years. And it's at a distance of about 500 megaparsecs. For reference, the distance between Milky Way-like galaxies is about 1 megaparsec. So this is a relatively large distance because these are relatively rare. Now, because these gravitational waves are carrying energy, this luminosity is a dE dt, that means that energy is coming from the binary, and the binary hardens together. The two components come closer together as they lose that energy. So the lifetime of binaries, we can calculate from that. We end up with something like 0.5 million years for the same mass of binary. That is 5/3, and the same frequency to the minus 8/3. So this is a very long lifetime. Okay, so even though this binary is orbiting with a period of like 10 years, I think I said, it's going to be orbiting at that period for almost 1 million years or so. So these are very well in kind of a nice Keplerian regime. In other words, we don't have chirps like LIGO does. So we're really mostly interested in these steady pseudo-Keplerian orbits. Okay. What this also implies, because the lifetime at a given frequency is so long, this implies that there could be a very large number of binaries in every frequency interval. Probably should have kept that. So what we really end up being interested in is what's called a stochastic gravitational wave background. So this is just the ensemble of millions, billions, thousands of black holes distributed throughout the universe at different frequencies. And this expression tells us exactly how they're distributed in frequency, very steeply declining. So as they get smaller, as they get closer together, higher frequencies, they merge faster and faster and faster, and you have fewer and fewer of them. So in a incredible paper by Sturl Finney just down the road in 2001, never published, just put on the archive, we can write the energy density of gravitational waves over a logarithmic frequency interval. And we can relate this to a quantity that we call the characteristic strain, which I inconveniently skipped over describing. So characteristic strain squared. And what this characteristic strain is just HC. HC is proportional to the square root of the number of cycles of your wave times the regular strain. And this is frequency times observing time. And this is just a way of accounting for how your signal builds up over time. So this characteristic strain is what you can plot on a sensitivity curve and say, hey, is this above or below the noise? Very convenient. So we can express this as, so the energy density of gravitational waves is just going to be the number density of binaries producing gravitational waves as a function of redshift multiplied by the amount of energy they produce over a logarithmic frequency interval, redshift the energy, and then integrate over redshift. So this is actually like a really subtle argument that the present day energy density is the summation of the integrated gravitational wave emission from all of history leading up until now. It doesn't have anywhere to go. The universe is isotropic and homogeneous, so it has to be here now. Just redshift it. But it's really cool. One thing I'll very quickly note is that this dE, this distribution of energy over frequency, if we were to write dE dF, we can write that as dE dt. Again, that's our gravitational wave luminosity multiplied by dt dF. And this tells us how long binaries spend emitting at a given frequency. So what's implicitly happening here is that every binary instantly evolves over all frequencies, deposits its gravitational wave energy, and we add that up into the background. So basically, most of what I do is explain why we really need to do this carefully. And that's all I'll have time to say about that. Yeah.
Just quickly, is there an argument for why none of these gravitational waves get absorbed by things in the universe?
Oh man, that's a hard one. I mean, I think it's mostly just because the coupling coefficient is just so incredibly small. What is it, 10 to the minus, yeah, whatever. It's extremely small coupling between them.
But that's also why they're so weakly emitted, so they're not some overall scale images.
But you need two of them. So you need one for the emission and then one for the absorption, as opposed to just one for the emission. Yeah.
I'm slightly confused about what goes into this EGW. So is also primordial gravitational waves, all the things that have been produced?
Yeah, that's another great question. Yes, if you want to do things properly, you should be taking that into account. I am only talking about binaries, astrophysical binaries produced from galaxies, stars, whatever. Yeah, that's a whole other topic.
Fine, but I'm guessing maybe you have like a different measurement in this. Is this your argument here? That I don't care about those for now because I can measure those separately.
No, not really. They're largely degenerate. It so happens that the properties that we predict from binaries seem to mostly a priori. Well, I'll come to this a little bit. They mostly match up with our observations. So it's a natural explanation, but we have not yet confirmed whether this is true, and that's not necessarily trivial. Yeah.
When does most of it occur?
Like what, redshifts?
Well, so there's this contribution to the dE.
Yeah. Mm-hmm.
When does most of the contribution occur?
Yeah, so it depends on like what frequency we're looking at, combined with the redshift distribution of binaries. But most of the energy is deposited as the binary gets towards the very end, just before coalescence. So the amount of energy deposition gets higher and higher as you go to higher frequencies.
I'm asking it somewhat different. So
Okay.
if you look at like the black body radiation, almost all of it came from like a certain time in the evolution of the
Which
universe.
redshift?
Yeah. Okay. Right.
And
So
does
yeah.
this come like uniformly
Yeah.
all for the last 15 billion years, or was it mostly done
Yeah, so from
14 billion years ago and it's just
Right.
kind of...
Yeah, from an astrophysical perspective, it's relatively uniform, distributed from like redshift 0 to like redshift 2 or so. So in terms of cosmology, the very recent universe. So this is
This is all recent stuff.
yeah. So what these massive black hole binaries come from is two galaxies merging together, and so you need to wait for these galaxies to grow to become large enough to host these very massive black holes, and then you need to wait for them to merge, and then you need to wait for that the binary to form after that merger, and then evolve to small separations. So if you look at that, it's probably mostly from redshift 1 to 2 or so, which is like 10 billion years,
Okay.
ballpark. Yeah.
And the new stuff from JWST, that there's so many huge
Oh boy. Yeah.
galaxies at early times, doesn't
Yeah.
change that.
Probably not drastically, but I don't think there are great models piecing all those together quite yet. Yeah. Great questions, man. Okay.
You got one more.
Yeah. Sorry. Please.
Maybe
Yeah.
a simple question. Is there any concern about the isotropic background of the gravitational waves for, like, say, Sag A, whether or not there's any perturbation to that?
Totally. Yeah. I think this isn't something that's been fully settled. Chiara just had a paper out on this recently, but likely for these types of distances, the universe is almost perfectly uniform at that point. So where these sources are distributed should just be kind of shot noise Poisson distributed. But there is some possibility that there could be correlated structure. Quick one?
On the same topic with the isotropic, did you ever calculate dark energy into any of your equation or in the...
Totally irrelevant for these calculations.
Well, are you planning to bring it in or not?
It's irrelevant for these calculations. Okay, so we're making an assumption about how this energy is deposited, but what's usually done is you assume that this happens from only gravitational wave evolution. So this binary forms, it evolves and coalesces purely due to gravitational wave emission. In that case, there's a very nice expression for this DEDF that we can just plug in. And what Finney showed we get out is the following. So little space on these things, on this enormous chalkboard. Okay, so I introduced the chirp mass here because we really need to be looking at how different massive binaries produce different amplitudes of gravitational waves, but we integrate over that distribution of masses and redshifts. This is our weighting for the energy deposition, but the crucial part here is that our characteristic strain spectrum looks like f to the minus 4/3. Okay, so that is this kind of universal prediction for purely gravitational wave-driven evolution. And so what that looks like, frequency here, characteristic strain, f to the minus 2/3, because this is just normal characteristic strain. We're observing, pulsar timing arrays have observed for tens of years, so this is something like 2 nanohertz or 1/16 years in our recent data set. Somewhere out here we have 1/a which is about 30 nanohertz. And for various reasons, this is kind of where we normalize our gravitational wave amplitude. You've got to measure it somewhere. That's where we do it. And so the observations from pulsar timing arrays, they end up looking something like that. Okay. So we have very large error bars, especially looking at characteristic strain, but broadly they kind of follow the prediction. The slope of this is a bit flatter, actually quite a bit flatter than what we would naively expect. And at high frequencies, we're dominated by noise. I'm trying to indicate our posteriors extending to 0 there. So in particular, what we measure is an amplitude of something like 2 to 6 times 10 to the minus 15. And our spectral index, which we might call alpha or gamma, it's something like minus 0.4 to plus 0.1. And the prediction is minus 2/3 for reference. Okay. So this is the amplitude that we get measured at 1 over a year. Spectral index is a bit flatter than expected. And now the false alarm, so we see this signal in all of our different pulsars, 68 pulsars on the sky. The false alarm probability for that to happen, for having this common spectrum process, is something like 10 to the minus 12, I think. Extremely small. So there is definitely a common spectrum process across pulsars. We're fairly confident that it's Hellings and Downs correlated specifically, which is the smoking gun for gravitational waves. Okay? So now, the last thing that I want to talk about.
Can I just ask, in terms
Yeah,
of
yeah.
accumulation of data, obviously
Yeah.
this one cares, we both care about accumulation of data.
Yeah.
How does the significance of the measurements change with time for the two different measurements?
Interesting.
Is it the same way with time?
I'm not positive, actually. I think they should. I think they should.
Or just significance growth with time, if it's real?
Yeah.
Okay.
Yeah, I mean, growing significance on this doesn't really help anymore, but I think the scaling is still the same. Yeah.
Thank you.
Yeah, I mean, it does get it. So the tricky part is that it gets into the subtleties of how you model the noise in each pulsar, and that has a fairly strong time dependence on it. Okay, so yeah.
So in that signal, that one that goes below and back above, do you integrate like overall frequencies of this?
Yeah, so there's a variety of different ways of doing that. In our main result, we use the first 5 frequency bins, which is the only place where we have a significant Bayes factor, significant evidence for Hellings and Downs. But in other words, we kind of integrate forward until the data suggests that we're not getting more evidence. Okay, so the last thing that I want to emphasize is that this measured amplitude is actually a lot higher than we were predicting. And actually, some groups thought that they had strongly excluded this high amplitude many years ago. And I think the best way of, before I get to that, okay, so also in this Finney 2001 paper, he pointed out this really cool thing. So this is essentially the rate of mergers of these binary systems. And each of those mergers is 2 black holes. They merge together, and they produce a remnant black hole. And actually, this final remnant mass, that's M1 plus M2 minus some delta M from gravitational waves. There's some energy loss from the system due to gravitational waves. But still, you can relate the amount of energy and mergers to the present-day remnants of masses. So let me actually just write that out. So the total energy density of gravitational waves, we'll just integrate over that same expression. We can write this as, so now we need to break up this number density a little bit more. QdZ, so we have some efficiency factor for how much energy is emitted, how much of the rest mass is emitted in gravitational waves, times that mass growth, the equivalent energy, integrated over redshift. And that gives us the present day mass density of black holes at redshift 0 times c squared times the fraction of mass grown through mergers as opposed to something else, and then this efficiency factor averaged over redshift. Okay? So this just requires measuring how many black holes there are in the local universe as a function of mass, or how much mass of black holes there is, and that's tied to the gravitational wave emission. So, in a recent paper by one of our organizers, Gabby Sato-Polito, along with Matthias Zaldariaga and Elliot Quadard, showed that this can actually be calculated in a much more elegant way by essentially doing the reverse of this. So we use this firm anchor point of our local measured black hole masses, and then we wind that backwards into our component masses over here, and you can keep winding backwards, etc. And the benefit of casting things in this way is you can make upper limits on the gravitational wave background that absolutely, most optimistically, how much gravitational waves can you produce? So kind of the very nice expression that they end up with, we can write our characteristic strain spectrum as 4 pi 3c squared. So the same spectrum, of course, and then we essentially we break up this merger rate into separate components. So we have some distribution over redshift, probability of z. Then we have some distribution over mass ratios, q over 1 plus q squared, some q distribution, and then finally this dm1, and that gravitational wave amplitude normalization there over dm1. Okay, so the redshift distribution, the mass ratio distribution, you can come up with like pretty nice models for that, and your sensitivity is actually fairly weak to them. So really what's most important is just this number density as a function of mass, so how many objects of a given mass you have. And the way that they calculate this is also very elegant, that dm1 is the number of galaxies with a given velocity dispersion. And this velocity dispersion, there's reasons for why we do this. There's a whole industry in measuring the velocity distribution function of galaxies, but take my word for it, it's very effective in measuring galaxy properties and relating them to black hole properties. So we have number of galaxies as a function of velocity dispersion times the relationship between velocity dispersion and black hole masses. So at the end of the day, we have very well-studied empirical distributions for this velocity dispersion function, and then also the relationship between the velocity dispersion of a galaxy and the mass of its black hole, something like that. You plug those two together into this equation, and then you get out just a very clean upper limit on your gravitational waves. And I really like this plot from Gabby. This is the measured amplitude of the gravitational wave background, something like 3 times 10 to the minus 15. We have different pulsar timing arrays to make different measurements. Then our predictions from the upper limits of what this should be are down here. You explore different model variations, and that's down at about 1 times 10 to the minus 15. And this is why we're here the last 2 weeks, is why is this? How do we fix that? What does it tell us? And what are the consequences for the near future? There are a couple of ideas. I see I'm already over for that. But you really don't have much wiggle room in these arguments. So really, most of what it comes down to is that these masses need to be measured incorrectly. The number of galaxies as a function of some measure of their size is measured incorrectly. Or there are black holes hiding somewhere. But we'll try to get better answers soon. Thanks.
More questions?
Very true. Can you repeat the numbers? I can't read.
Oh, sorry. Yeah. So I mean, there's a large range on the uncertainties, but something like 3 times 10 to the minus 15, and the prediction is about 1 times 10 to the minus 15. Yeah. And so, I mean, that definitely drums up the excitement, but I should emphasize that our error bars on this spectrum are extremely large, and the error bars that we usually look at don't really take into account all of the systematics. The page of notes that I skipped over, I don't know why I thought I would be able to talk about those, was about some of the noise modeling that really has a strong effect on the amplitude that we measure from this. So something that we've been talking about is how do those affect things.
Does it get worse if you account for the fact that black holes grew by green gas and not only by merging?
No, that actually makes it easier. Wait, no, sorry, that makes it worse. That absolutely makes it worse. Yes, it does. Yeah.
This probably happen at different epochs, so these probably are emitted at very low redshifts versus the growth by accretion will happen redshift 2-ish. So you
It's okay to say, yeah, maybe black holes in the recent universe grew primarily predominantly in emergence.
Okay, let's ask a different question. Tessa.
Yeah, I was just wondering, is there some other kind of, like, is it clear that it's not coming from, like, dwarf galaxies or some, I'm not an astrophysicist, so I have no idea, but
Yeah.
does it have to be black holes that you're measuring?
So there is a lot of interest, and could this come from cosmological sources? So this is usually very early universe, inflation, crazy particle physics stuff. So that, I mean, that could be the background. We have not excluded that yet. And then it could have any amplitude that we want, basically. It's also possible that that's making some sort of contribution to it. But in terms of astrophysics, there really isn't anything else. It would, I think there's really nothing else besides supermassive black holes. And it's even, we can even say it should really be supermassive black holes at particular mass ranges and redshifts. It's hard to even deviate from that too much.
In principle, could we gain something by recycling mass? Spinning black holes can shed some of their mass, and then they could reaccrete it.
They can.
It sounds far-fetched, but
right. Oh, you mean like extraction of energy from highly spinning black holes? I think that's vanishingly small from these contexts.
So the upper limit was published after the data, right?
Which upper limit? Oh, yes.
What you
yes.
described as a robust theoretical, with some phenomenology argument, upper limit.
Yes.
You guys didn't know about when you published.
That's correct.
Okay. It's always interesting.
Yeah, but I mean,
sociology, but if the opposite had happened.
In 2015, there was a published PTA upper limit of 10 to the minus 15 also, back in 2015. So there's definitely been a lot of evolution about both the measured amplitude and the theoretical constraints.
I'm still a little bit fuzzy on the type of black holes that are missing. So you said
Yeah.
some black holes. What type of black holes would these be?
I'm really just spitballing here. Like that's just one of the only ways that you can kind of sneak something into here. So in general, we have, I shouldn't have erased my beautiful galaxy picture. Yeah, we don't need another one. You have some galaxy, right? And these massive black holes, they live in the centers of those galaxies. So basically every galaxy that we look at, there is one and no more than one. But yeah, exactly. But it is conceivable that maybe you have some pairs out here, and those are not the ones that we measure and constrain. So you're adding new black holes into this system that don't fall into our mass density of black holes at the present day.
Okay, thank you.
Yeah. I mean, unlikely.
Yeah.
So then what sort of independent signature would you look for to see if these guys are there?
Great question. So, sorry, for these in particular?
Yeah,
those are very hard to detect. So once your massive black holes are not at the center, they're ineffective at accreting gas. And if they're not accreting gas, they're not producing emission. So they're hard to see. One exception to that is tidal disruption events, which is something that Stephanie Camosa is an expert on. So every once in a while, a star might pass close to these and get shredded apart and produce a flare. That might not work at the masses that we're talking about, but it's still a way of probing, do you have these wandering massive black holes out there? Lensing could also be another way of doing this, probably just within our own galaxy, but even within our own galaxy, ruling out these massive black holes is extremely difficult.
Chris?
The stellar density in the neighborhood outside the core also is really low. It's also possible to actually see one of them in how many galaxies.
One of these stellar disruption events, also probably pretty low. It can depend somewhat on how these got out there. So if these were deposited here through galaxy mergers, which is the main channel for producing these binaries, they can bring along cores of stars with them. And there's some reasons to expect that in this exterior tidal potential, you could actually increase the tidal destruction rate of those bound stars around here. It's also possible that following a previous merger, the black hole is kicked out by gravitational wave recoils, and that black hole with a small bound clump of stars could also have a heightened TDE rate. If you have just some wandering black hole out there, yeah, general TDE rate would be very, very low. Yeah.
Okay, well, thank you very much, Luke.
Sure.